and welcome to the BCPy2000 demonstration, now updated for Python 3.6, featuring a completely new open source flexible real-time visual stimulation module, PsychoPy. In this video we will first go over what BCPy2000 is, what BCPy2000 is, why you may want to use it, an in-depth installation process, a demonstration of our Triangle app boasting a wide range of features, and a tutorial on how you can create your own PsychoPy experiments within BCPy2000. BCPy2000 includes software tools that can acquire and process data, present stimuli and feedback, and manage interactions within outside devices. BCPy2000 is a real-time system that can synchronize a wide variety of biosignal and input devices such as mice or eye trackers. It has several modules which manage data importing and exporting in common file formats. BCPy2000 allows for rapid, flexible development of brain-computer interface systems utilizing the BCPy2000 framework. While it is based on and hosted on the BCPy2000 project, this implementation is carried out in Python, taking advantage of various high-level packages such as PsychoPy for stimulus presentation and NumPy and SciPy for signal processing and classification. Being that Python is a widely used language and it has a much lower bar of entry than C++, making it the perfect alternative for people who would like to use it, while still retaining the modularity and comprehensive range of EEG acquisition modules which BCPy2000 supports. This implementation of BCPy2000 is built on an implementation last updated in 2009, which utilized Python 2.7 and VisionEgg. However, both Python 2.7 and VisionEgg are now deprecated, so we re-implemented it in the newest version of Python, which has a portable version and which also supports PsychoPy. First, we'll shortly go over the prerequisites for this project. You're going to need BCPy2000 and our portable Python package. While compiling BCPy2000 following the instructions on our wiki page, you can compile for either 32-bit or 64-bit systems, as we now support both. Once you have reached the CMake file by going into BCPy2000 and build, and then double click on configure, you'll be prompted to build BCPy2000 and contrib. This is where your BCPy2000 project folder will exist. Once you've generated your project, you're going to want to open Visual Studio 2019. And build the solution for the first time. Once you've already built the entire BCPy2000 solution, if you ever want to make any edits to the Python application or signal processing or source applications, then you can simply just rebuild the individual projects. All three projects have a shared Python filter and Python wrapper class. This is where you'll be doing the majority of any editing when you want to change the interface between the C++ code and the Python code. After building the Python application, the Python source, and the Python signal processing modules, You're going to want to exit out of Visual Studio 2019, go into your source folder, your contrib folder, and then BCPy2000, and then demo. And in these folders, you contain different files which you need to then copy over to your main BCPy2000 directory. These files include the actual executable files, the parameter files, the data files, and the batch files. For the purposes of this demonstration, I've already built and copied the necessary files and placed them in their respective folders. Next, we will unzip and set the path for our portable Python package, which can be found under our wiki entry. Make sure that you're downloading the correct version corresponding to the version of BCPy2000 which you have built. Now that you have unzipped your Python version, we have to add it to the system variables. Go to Environment Variables, go to System Variables, create a new system variable, and for the name you want to have Python home underscore BCI 2000. And you're going to want to put in your portable Python directory, press OK and OK. Make sure that you use that specific file, that specific path name, so that it does not interfere with any other Python installations you may have already had installed. Under your portable Python installation is where you will have the vast majority of the important code where you will want to do your customization. To access that, you'll want to go into lib, site packages, and then edit whatever packages you want. For example, BCPy2000 contains packages for the console, the generic application, and generic Py. You can also add new Python packages by going into command line, going to the directory in which your portable Python is found, and using this command, python-m pip install and whatever package name you would like to put in. Now that I've shown you how the Python portable package works and how to build your BCPy2000 modules, I'll go on to show a demonstration. For our demonstration, I will go over the triangle application included with BCPy2000, which asks the user to imagine moving their hands or feet in order to guide a cursor into one of three corners of a triangle, while simultaneously giving the user color and sound feedback, which corresponds to an imagination task and a sound. All we have to do is open up the triangle app batch file, which is located under the batch folder. We click Python demo 1 triangle P3, and we will be presented with the operator. In the operator, we can set the configurations. In here, we can set a lot of different parameter files, such as visualize timing and visualize brain signal. These are two very useful parameters. We can also specify the signal properties. We can change the block size, the sampling rate, and the number of channels, along with a lot of other useful properties. We can also specify the location and how data is stored. And we can also edit variables pertaining to the actual Python application, such as showing the signal time through the state monitor. We can also save these parameters by clicking Save Parameters and then going into the parameter folder and saving any changes that we made to the parameters in the configuration. Once we're happy with our configuration, we can set the configuration and we can start the application. So here you'll see the BCPy2000 specific timing window, and here we'll also see the state monitor, which provides us with valuable statistics for developers. So for example, we can see the current block, the current trial, the phase that we are in, and the frame rate as hertz. And we can also verify this with the BCPy2000 specific timings. For our demonstration, I'll go over the triangle application included with BCPy2000, which asks the user to imagine moving their feet or hands in order to guide a cursor into one of 3 corners of a triangle while simultaneously giving the user color and sound feedback, which corresponds to an imagination task and a sound. All we have to do is open the triangle application, which is located in the batch files named Python Demo 3 Triangle Python 3. When we open it, we can now see the operator and the source, signal processing, and Python application are running. We can do things in the config. For example, we can visualize timings, we can visualize raw brain signal, we can go into the source and specify the number of channels, the sample block size, the sampling rate, and many other variables. We can also specify the session name, session number, and the ID and the file format. We can also go into the Python specific configurations. So for the Python application, we can see the description of the triangle application. We can show a timestamp based on the number of processed samples, the trials per block, and the blocks per run. We can also save these parameters and then load them later for easier configuration. For now, I will just demonstrate the triangle with a visualization of system timing and a timestamp of the number of processed samples. So what we are going to do is set config, and now we have this timing window as well as our operator and our actual application. So we can click start and we can see the application is running with the state monitor, and this corresponds with our latencies in the timing window. Because we enabled state monitoring, we can see the performance of our application and see it go through each block of data and monitor the frame rate. For our demonstration, I'll go over the triangle application included with BCPy2000, which asks the user to imagine moving their hands or feet in order to guide a cursor into one of 3 corners of a triangle, while simultaneously giving the user color and sound feedback, which corresponds to an imagination task and a sound. All we have to do is open up the triangle application batch file. Which is called Python Demo 1 Triangle P3. In here we'll see the operator, and in the operator we can open the parameter configuration tool. Here we can set BCPy2000 specific parameters such as visualizing the timing window. We can set the source signal properties such as the number of channels, the block size, and the sampling rate, along with a lot of other artifacts. We can specify how the data is stored, and we also have access to the Python specific configurations such as the description, the time monitor. We can show a timestamp based off of the number of processed samplings, the trials per block, the blocks per run, and all of these parameters can be saved into a parameter folder that we have here for easy use later. So what we'll do is we'll set config, and in the bottom right you'll see the BCPy2000 specific timing window, and you'll also see our state monitor, which is implemented in Python. So what we'll do is we'll go into the operator and we will start the task. Here you'll see the triangle application running through its phases. We can see the current phase, the current block, the current trial, the target class, the phase, and the frame rate measured in hertz. All of this can be double checked with the BCPy2000 specific timing window, and it all checks out. And because we enabled the state monitoring, we can also see the performance of our application as it goes through each block of data and monitor the frame rate. Now I will go over how the triangle application works and explain how you might structure your own BCPy2000 application. First, we'll go into the actual location of the file, which in this case is the triangle application for PsychoPy. We open that in whatever text editor you prefer, and the first thing that you will see are the imports. These are the packages necessary for a wide variety of functionality, including the BCPy2000 interface, the PsychoPy visuals, native timing, sound, and complex numerical calculations. The structure of each BCPy2000 Python application is composed of one class containing 9 separate definitions. Our first definition is the description of the application. This is simply where you'll give a short description of what your application does. Next, we have the construct. The construct defines all of the parameters and states which you want to record and store for your application. In this example, we see that under our parameters, we have artifacts such as screen ID, cursor feedback, and audio feedback. These are things which comprise our application's functionality. Next, we have our states. States are essentially event markers. Each state reflects important events during our real-time system operation and are saved to the data file with each associated sample. Our next important definition is our pre-flight phase. Here we set up our screen with which we will later create our visual stimuli, and we specify things like our screen size, screen ID, and we instantiate the actual screen. Now that we've set up the window, we have to initialize our stimuli. First, we'll calculate how big everything is, scaled to the window size. Then we will draw the stimuli here, including the 4 triangles and the arrow. We will also set the background of the stimuli to black, and then we'll register them with the framework here. We'll also set up cues so that we can tell the subjects what actions they must take. And here we'll also tell them which sounds will play. And then here we add state monitors, which will allow us to have the option for developers to ensure that the application is doing what they want it to do. Developers can use these state monitors to check a myriad of internal components, such as the current block data, the current trial, the samples per second, and the frames per second. Our next section is the start run section. This starts the visual stimulus and is called when the start button is pressed, and this is where you will want to set your stimuli's on state to true. Our next definition is the phases section of the application. This is where we define phases using calls to self.phase and self.design. These phases correspond to the states which we set up in the constructor definition. Here we can set the duration and name of each phase, as well as what the next phase is supposed to be. Next, we have the transition phase. This will present the stimuli and update state variables to record what is going on. Our next definition is processing. In this definition, we process each new signal packet and then record its data into the data file. Finally, we have the stop run definition. This is called whenever we close the application or reconfigure it. Here, all we have to do is turn off all of our states and stimuli. Next, we're going to take a look at the source module for our triangle application. So in this case, it's the trefoil source located in the Python folder, much the same as the application. Here, all we do is generate an artificial 3-channel signal that makes the cursor visit each corner in turn, and the signal processing module passes this through unchanged. First, we define how we initialize these signal sources, and then we define how to process them. Now that we've seen all of the things that you can do with BCPy2000 and how to implement them yourself with our triangle application example, let's go over an example P200 event-related potential task with a live subject to demonstrate the modularity and flexibility that the BCPy2000 platform affords us. In this experiment, we have the subject simply observe 20 trials of a flashing white box at a half-second intervals, interspersed with random red boxes. This would be an example of an oddball paradigm which evokes event-related potential responses in the subject. The subject's raw brain signals are acquired through the GUSB amp amplifier, which are then displayed on the left screen. Then this source is passed to the Python signal processing module, which, for the purpose of this experiment, simply passes the data to the application. Meanwhile, the application module is displaying the stimuli. Here we have a demonstration of BCPy2000's modularity and resultant flexibility. In this experiment, we have a BCPy2000 application and signal processing module working with a C++ compiled GUSB AMP signal source module. Because all BCPy2000 modules communicate locally over TCP and UDP, you can seamlessly pick between whatever modules you would like to use for your purposes. For example, you could choose to have a C++ signal source module for your amplifier supported by BCPy2000, pipe that through a MATLAB script which does real-time signal processing, and display all of the stimulus and feedback through a BCPy2000 application module. This concludes the BCPy2000 video. You can find more information and specifics on the integration of BCPy2000 and BCPy2000 on the BCPy2000 wiki, to which the link is provided in the description below. Thank you.